Alrighty, we are live. Hello and welcome back to week 5 of Chem 305 summer session. Edition. I am back in my natural habitat, so to speak. You can see I have my my Mike Mignola and Duncan Ferretto art hanging behind me. Whoa, where's my mouse? There we go. Good afternoon to you, Parthana. What are we doing? It's Wednesday. Wednesday, week 5. We're in the middle of chapter 7, actually nearing the end of chapter 7, talking about gas laws. And a couple things. One thing that I want to point out is that, as we all know, exam 2 is coming on Friday. It will be on chapters 5 and chapter 6. So Lewis structures, geometries in chapter 5, and then a lot of stoichiometry in chapter 6. And I want to point out that you may have noticed, as we've been talking about gas laws, that we've been doing a decent amount of stoichiometry as well. And that is not by accident, that is on purpose. Even though chapter 7 is not on the exam, I wanted to make these lectures as relevant and as pertinent to you as possible, and so I've been including a lot of stoichiometry examples so that you can so that hopefully, even as you look at material that's not on the exam, it'll be good kind of preparation for taking exam 2. Prathana, good question. When is exam 3? Let's consult the master list. Let's see. I believe it's in a couple weeks. Exam 3 opens. So if you're wondering, exam 3 opens, and this is in the syllabus, opens on Friday, July 24th, and closes Sunday, July 26th. So we're kind of alternating weeks. So we're taking exam 2 this weekend. Next weekend we get a week off, and then come back for exam 3. So that is far in the future. Well, it's about 2 weeks in the future. I haven't started writing it yet, but you can bet that that's what I'll be working on this weekend. All right. We left off lecture yesterday with a gnarly problem. All right. A problem that I said we didn't have enough time to do. However, I wrote it out and in hopes that you would take a crack at it, and now we can work it together today. So I'm going to go ahead and read it. This is the example problem. Nitrogen trihydride gas decomposes into nitrogen gas and hydrogen gas at 212 degrees Celsius under 0.73 atmospheres of pressure in a 15-liter metal cylinder. Part A, balance this chemical equation. Part B, if all the nitrogen trihydride completely decomposes, what is the total pressure in the cylinder? And there's a hint here that we'll circle back to later, but first, let's start by balancing. We have all covalent compounds here. We have nitrogen trihydride gas decomposing. This is a gas decomposing into nitrogen gas, which is a diatomic, plus hydrogen gas, also a diatomic. Now we need to balance two elements here, nitrogen and hydrogen. On our reactant side, we have 1 and 3. Product side, we have 2 and 2. So the only way to balance nitrogen is to multiply NH3 by 2. This will balance nitrogen and change hydrogen. So now we have 2 nitrogens on both sides of this equation and only 6 hydrogens on the reactant side, 2 on the product side. And then we need to balance our hydrogen, so we multiply H2 by 3. Now we have 6 on both sides of our chemical equation. All right, so that is part A, right? A balanced chemical equation for this reaction. All right, now let's take a look at part B. All right, now we're told that it decomposes completely, and we're asked what is the total pressure of hydrogen in the vessel. We're asked to find the total pressure all right, well, the total pressure, and then we were given a hint. We were told, note that there are 2 gases present in the cylinder, right? It decomposes into hydrogen gas and nitrogen gas. So here our total pressure is going to be equal to the pressure of N2 plus the pressure of H2. All right, it's going to be these 2 pressures combined. Now what are we given here? What are we given in this problem? One thing I can see is we're given a volume. We're told that this takes place in a 15.0 liter metal cylinder. So we know the volume that's going down. We also know the pressure, well, I should say, we know the pressure of NH3. The pressure that we're given is the pressure of the ammonia, the nitrogen trihydride, in the cylinder is 0.73 atmospheres. And we also know the temperature that this reaction takes place under, 212 degrees Celsius. Now, it's just a good idea to always convert your Celsius to Kelvin, because anytime you're using the combined gas law or ideal gas law, you're going to have to do it at some point. So why not get this out of the way on the early side? So we know the temperature inside the cylinder is 485 Kelvin. All right, now, there's one additional piece of information that we always know, and it's always worth writing down. We know what the ideal gas constant is, R. R is equal to 0.0821 liter atmospheres per mole Kelvin. Okay, we've got all of our givens down. Let's see how we can connect them to what we're after, what we're trying to find. Now you'll notice, to find our total pressure, we need to find the pressure of nitrogen plus the pressure of hydrogen, right? We need these 2 things individually. And we could say that the pressure of nitrogen times its volume equals the moles of nitrogen times R times T, right? We could say the same thing for the pressure of hydrogen, right? Pressure of hydrogen multiplied by its volume is equal to the moles of hydrogen times R times T. We can solve for the pressure of each by dividing both sides by the volume, right? That'll cancel on the left side of the equation. So we isolate pressure. So the pressure of nitrogen gas is equal to the moles of nitrogen gas times RT over V. Pressure of hydrogen gas is equal to nRT over V. And we can take these, right, and plug them in to our algebraic expressions here. Right? We know what pressure of hydrogen is equal to. We know what pressure of nitrogen is equal to. All right? And we're going to do this together on the next slide. All right? So, as we plug in this information, our total pressure, which I'm just going to write as PT, total pressure, is equal to the moles of nitrogen gas times RT over V plus the moles of hydrogen gas times RT over V. And you may notice that R is the same because they're in the same vessel, the same metal cylinder. Our volumes are the same, and because they're products of the same reaction, the temperatures are the same. So we can factor out RT over V because they're present in both expressions, and just put RT over V times the moles of N2 plus the moles of H2 are equal to the total pressure. All right, total pressure is equal to this expression. And remember, we know R, we know T, we know V. So we just have to find two things, right? We have to find moles of nitrogen and moles of hydrogen. Now, how can we possibly do that? Well, there is one piece of given information that we have not used yet, right? And that is the initial pressure of ammonia, NH3. The pressure of ammonia times the volume is equal to moles of ammonia times RT. Why is this significant? Well, we know the pressure of ammonia, we know the volume, we know R, we know T. We can solve for moles of ammonia and then use our balanced chemical equation to determine moles of nitrogen and moles of hydrogen. So let's solve for our moles of NH3 and then do a little stoichiometry. We'll come back to this expression, plug it in for our total pressure. All right, so first step, if we're solving for moles of NH3, we need to divide by RT. Right, this gives us moles of nitrogen trihydride or ammonia is equal to the pressure of ammonia times the volume over R times T. Now our pressure was 0.73 atmospheres. Our volume was 15.0 liters. R is always the same, it's 0.0821 liter atmospheres over mole Kelvin. And then our temperature was, let me find it, after the conversion, there we go, 485. 485 Kelvin. So units wise, Kelvin cancels Kelvin, liters cancel liters, atmospheres cancel atmospheres, and we that's it. We only have moles, so one remaining unit, which is good because we're solving for moles of NH3. We can keep 2 of our sig figs based on our pressure. So let's see what this holds. So we got 0.73 times 15.0 times 0.0821 times 485. No, I'm sorry. I punched it in wrong. 0.73 times 15.0 divided by 0.0821. Oh man, my calculator's being all weird. Divided by 485. All right, so our moles of ammonia, let's see, we can only keep 2 sig figs, are 0.27 moles after you round. All right, now we can take this 0.27 moles of NH3 and we can use stoichiometry to convert it to moles of H2 and moles of N2. All right? So if we're converting to moles of N2, our balanced chemical equation tells us 2 moles of ammonia produces 1 mole of nitrogen. This comes out to be, let's see here, 0.27 divided by, 0.27 divided by 2 is 0.14 moles of N2 after rounding. And we do the same song and dance. We take moles of ammonia and convert to moles of hydrogen. And here, 2 moles of ammonia produce 3 moles of hydrogen. So we take 0.27 divided by 2, multiply by 3, and we get 0.41 moles of H2. All right, now that we know moles of N2 and moles of H2, we plug it into this equation and solve for our total pressure. All right, so our total pressure, just rewriting it, is equal to here we go, RT over V times moles of hydrogen plus moles of nitrogen. All right, R, I'm actually going to leave this symbolic for just one more turn. You will see why, just it's less writing. I'm going to plug in my moles for nitrogen and hydrogen at this point. All right, moles of hydrogen, 0.41 plus 0.14. It's an interesting symmetry. I forgot to write my units. All right. Oh, sorry, I wasn't even thinking. Sorry. 0.41 plus 0.14 comes out to, oh goodness, Always fun when you drop your calculator. Comes out to be 0.55. All right, so total pressure is equal to 0.0821. This is our liter atmospheres per mole. I'm sorry, Brianna, that's funny. I normally remember to close the door when I'm lecturing, because normally there's like littles running around and everything. He's down for a nap, and the big ones aren't little. But my wife was like, "Why is your door open?" So anyways, yesterday was a guest appearance from the baby, and now the lady is officially shown up to class. It's who says it's not haunted. My 12-year-old's alert when she gets a text is that like creepy, like ooh, like paranormal alien type sound. And my niece, who's 3, heard it go off, and she was like, because we all went on vacation with my brother-in-law and sister-in-law and their kids. My 3-year-old niece heard it, and she's like, oh no, it's scary, there are ghosts. And I was like, it was just, might have been my favorite moment of vacation. It's scary, there are ghosts. Okay, let's see. So I've got to grab, oh, there it is. Our temperature is 485 Kelvin. And then over our volume, which was 15 liters. And this is all multiplied by our total moles, which is 0.55. You'll notice that moles cancel moles, Kelvin cancels Kelvin, and liters cancel liters, leaving us just with atmospheres, right? Pressure units. So we have 0.0821 times 485 divided by 15 times 0.55. All right, and so our answer, the total pressure, rounded to 2 sig figs, is 1.5 atmospheres. Oh my goodness, that's awesome. The haunting of chemistry lecture. It's the ghost of the avocado who lives in the machine. Okay. That's okay. So that is the end of that problem, and this is why I didn't want to try it with what was that? 10 minutes left in lecture, because here we are, 24 minutes in, and we just finished it. All right, now. This problem was very clearly next level, much harder than the ideal gas law problems that we worked before, and there's a reason why it was a little harder, and that is because to solve this problem, we had to use our final gas law for the chapter, and we didn't even know it yet. We hadn't learned the law, but we applied its principle organically to the problem. And so congratulate yourselves. So many steps, Susan. So many steps. If you're deeply confused, we can totally hit this, unpack it more in office hours. And the good news is this won't be on exam 2, but this concept will be on exam 3, because it's a very important gas law. It is known as Dalton's law. Of partial pressures. All right, Dalton's law of partial pressures. What Dalton's law of partial pressures states, it's a relatively simple idea, and it simply says that for a mixture of gases, so for a mixture of gases, the total pressure is equal to the partial pressure of the first gas plus the partial pressure of the second gas plus ... the partial pressure of the last gas, or the nth gas in the mixture. So right here, these are just all gases in the mixture. All right, those are all the gases in the mix. So, for example, when you look at the problem we just did, where ammonia gas decomposes into N2 and H2, the total pressure of the final mixture was equal to the partial pressure of N2 plus the partial pressure of H2. And so what we had to do, and what we did, is we had to find the partial pressure of N2 and the pressure of H2, then add them. We did a little more fancy algebra in our execution of the problem, but that's essentially what we did. We found our two individual pressures and then added them together to find the total pressure in that gas cylinder. All right, now again, you have some time to process this situation. This is all Chapter 7 material, which will not show up until Exam 3. So you have time to process it, to rewatch each step that we took along the way, and maybe viewing it through the lens of this equation might help you understand a little better. But for now, we're going to move forward. There's Dalton's law of partial pressure problems at the end of Chapter 7 for practice, if you want it, and we're gonna keep moving forward because we are nearing the end of Chapter 7. All right, and welcome, and it will be. So we have been talking almost exclusively about the gas phase, all right? And to close Chapter 7, which is technically about the gas phase, liquid phase, and solid phase, we are going to move on and start including some of the other phases, and we'll do this with a discussion of phase changes. All right, phase changes. So, we have three phases of matter, right? There are solids, there are liquids, and there are gases, all right? And when a gas, or, yeah, why not? When a, well, no, I'm going to start in the opposite direction. When a liquid becomes a gas, that process is called boiling, right? Whoa. Boiling or evaporation. Oh my goodness. Photoshop is being persnickety. All right, so when a liquid becomes a gas, we call it boiling. When a gas goes the opposite direction, when a gas becomes a liquid, we call this condensing, right? When you walk out in the morning and there's dew on the lawn, right, that didn't come from a sprinkler, you said, oh, there's condensation, right? Or when you blow your breath up against a windowsill and you see it get all foggy, you say there's condensation on the windowsill. So when a gas becomes a liquid, it's condensing. When a liquid becomes a gas, it's boiling. All right? Now, when a liquid becomes a solid, this is known as freezing. Right? We've all put water into our freezer, right? And so that it'll turn into ice. Liquids go into solids. That process is known as freezing. Solids becoming liquids, this is known as melting. All right, and the transitions, the phase changes between solids and liquids, we're more or less familiar with thanks to water. And even liquids to gases, we're pretty familiar with those too, at least with boiling, right? We do that with cooking all the time. Condensation, we may not think about it, but we're familiar with the process with dew, with breath, on the window, etc. But two processes that we don't really encounter in our day-to-day lives are the transitions straight from the solid phase to the gas phase, and the transition that goes straight from the gas phase to the solid phase. Normally we think like, oh, it's solid, goes to liquid, then goes to gas, but there are actually direct transitions between the solid and the gas phase. When a solid becomes a gas, this process is known as sublimation. When the solid goes directly to the gas phase. An example of this would be dry ice. You know how you can buy a block of dry ice and it melts and it melts and it melts, but there's no liquid, there's no water, that's why it's called dry. It's because a block of dry ice is not water, it's actually carbon dioxide. And carbon dioxide does not want to be a solid, right? Carbon dioxide wants to be a gas. So the reason why the block of dry ice shrinks is because the CO2 molecules are literally jumping straight from the solid phase out of the solid phase into the gas phase. Just skips the liquid phase entirely. All right, so that might be an example of sublimation you've perhaps witnessed or are aware of. Going from the gas to the solid phase, much less common. I'm pretty sure that nobody knows this unless you're super into engineering or whatever. But going from the gas phase to the solid phase, this is called deposition. It's a very commonly used inorganic process. Usually, it doesn't have to be inorganic, but often it's used with engineering microchip wafers, right? Like at Intel, those are built by doing a deposition. Yep, totally, Prathana. You definitely have experienced sublimation firsthand. Deposition. I'm trying to think if I have. Yes, I have seen deposition. There's one lab. Actually, there's a lab that you do in Chem 420, so first semester of OChem at FLC. If you take it, and if labs are even open, you'll actually do. There's a sublimation / deposition experiment. So if you do that, you'll be able to experience both of those transitions. All right. Now I have a question. I have a question for all of you. This is my question. My first question is, do you know the temperature at which water boils. Do you know that temperature? Oh, Prathana, interesting question. Distillation. That is a great question. So Prathana is asking, what is distillation? And distillation is a purification process that where a liquid is first boiled and subsequently condensed. So distillation, you boil something, it travels through a path, a distillation path, and then it's condensed back down, and this is done to purify things. Okay, awesome. Carolyn, you do know the answer to this. So do you say water boils at 100 degrees Celsius, right? Or 212 Fahrenheit. I've got another question. So you know when water boils, which is awesome. My second question is this. Do you know the temperature at which H2O condenses? Well, Brianna, you know the boiling point of your mind, or the melting point of your mind, then, I guess. And now that you know it, you know what to work on, right? So we know when water boils. Do you know the temperature that water condenses at? And allow me to be the first to tell you that if you know the first answer to this question, you know the second answer. Water condenses from a gas to a liquid also at 100 degrees Celsius. All right? When we talk about phase changes, there are melting points and freezing points. There are condensing points and boiling points. There's sublimation points and deposition points. And the same, each of these transitions comes in pairs. And the points, the temperature and pressure at which each one of these processes happens are the same in both directions. All right? This is the big take home. Whoops. Melting point is the same temperature as the freezing point. All right. The boiling point for a substance is the same as the condensing point. The sublimation point is the same as the deposition point. all of these points are equal to each other. And the reason why this is, each and every one of these points are the temperature and pressure at which both phases can exist simultaneously. All right? It means that the hottest temperature of water is the coldest temperature of steam. It means the coldest temperature of liquid water is the warmest temperature of ice. But each phase meets at the melting point slash freezing point, boiling point slash condensing point, sublimation point slash deposition point. All right? All of those things occur at the same time. Both phases of matter can be present under those conditions at that temperature and pressure. All right, this is why, for example, steam burns are much more dangerous than water burns. Because think about it, the hottest water can possibly get is 100 degrees Celsius, but that's the coldest steam can possibly get. So the worst water burn is the same as the gentlest steam burn, because steam is usually much, much hotter than 100 degrees Celsius. All right, so that is the point of all these melting points, boiling points, and freezing points. The direction of the phase transition, whether you're going from solid to liquid or liquid to solid, may change the name, right? Because if you're solid becoming a liquid, we say you're melting. Just like the Wicked Witch of the West. If you're a liquid becoming a solid, we say that you're freezing, right? The direction changes the name, but it doesn't alter the temperature and pressure. That is the same, no matter what. All right? Well, now, with that kind of idea and this groundwork kind of laid for phase changes, what they are, what they mean, I have another question. I have another question for us. And that question is this. If the boiling points of water is 100 degrees Celsius, then why will a cup of water evaporate at 25 degrees Celsius, right? If you leave a cup of water out just at room 25 degrees Celsius is like, it's like 74 degrees, right? It's more or less room temperature. So if you leave a cup of water out all week and you come back, it's going to be bone dry, even if the temperature never hit the boiling point. Why does that happen? And the answer to this question is tied up in a phenomenon known as vapor pressure. Oh, hang on one sec. My computer decided to freeze. Dude, water is weird. It is so weird. We'll get into it even more. Alright, sorry, hang on. My, every once in a while, my computer thermals jack out of control, and, there we go, okay. So the phenomenon known as vapor pressure. When my computer gets very hot, sometimes Photoshop stops responding. Vapor pressure is the reason why a cup of water will evaporate at room temperature given enough time. All right, let's talk about what is this thing? What is vapor pressure? Well, you got a cup, right? You got a cup, it's filled with water, and you got a bunch of water molecules all down up in the cup, right? Chilling out, liquid phase, it's a good time. Well, above the surface of any liquid, you're gonna have some molecules, same molecules as a liquid, but chilling out in the gas phase, all right? And sometimes they're all moving around, right? Kinetic theory of matter, all these particles are bumping around, moving around, hitting each other, hitting the walls. Sometimes you're going to have ricochets, where water particles will hit the surface of the liquid and bounce down. But sometimes you're going to have water particles escape, hit the surface of the water, and join that gas phase that's just kind of chilling above the surface of the water. All right. Same story with the little gas particles. Some of them will ricochet off the water, stay in the gas phase. Other particles will dive on in, rejoin the liquid phase. It's this constant kind of flux, equilibrium, moving back and forth between the two. All right. But so it's dynamic, it's moving, things are staying in the gas phase or joining the liquid phase, leaving the liquid phase, staying in the liquid phase, all that kind of good stuff. But one thing that'll happen is with an air current moving through, it'll come and blow away the particles that are in the gas phase, resting above the liquid. When that happens, let's keep our color scheme consistent. When that happens, all right, and the gas blows away all of the water vapor, it's disrupted the equilibrium. And now the particles in the liquid phase will start escaping to replenish the material lost in the gas phase as the wind blew it out. All right? But guess what? The wind's in constant motion, the atmosphere's in constant motion. It's going to carry these particles away. And the process repeats itself. All right? Our process repeats itself, and as more and more water particles leave the liquid phase to replenish the gas phase, our water level is going to drop. All right? And the same stuff starts happening. Different day, same stuff. We have more water particles leaving the liquid phase, joining the gas phase. The wind comes around, blows them away, until eventually, right, you wait long enough, and you will have a bone dry cup with no water left in it. All right? So the boiling point, remember, and this is true for this phase, for boiling. The boiling point is that temperature where both the liquid form and the gas form can exist at the same time. And when that happens, you heat something up to its boiling point, the liquid particles are gaining a lot of energy. They're going to start flying up into the gas phase like mad. But even if you're below the boiling point, there's still enough thermal energy for the liquid to start escaping the liquid phase, joining the gas phase, and as it gets pushed along by the motion of just the gas in the room, eventually your stock of liquid will be depleted. All right? That is why if you leave a cup over and then leave your house for a week and come back, it'll be bone dry. It's not because at some point while you were gone, your house became 100 degrees Celsius. It's because the vapor pressure was slowly removing water particles from the liquid phase, and the motion of the air in the room was pushing them along. The vapor pressure keeps replenishing the atoms in the gas phase above the liquid until all of the liquid water is gone. Cool? Okay, so that is vapor pressure. Yes. Say, that is exactly correct. Exactly. All right. Now, we are going to start. So we're still in chapter 7. This is the last hurrah. All right. We're going to start a discussion about something known as intermolecular forces. All right. And this will be this is really fortuitous because intermolecular forces deal a lot with the polarity of a molecule, and so this is a good thing to be touching on right before you all take your second exam. I'm just from here on out, I'm going to be writing intermolecular forces as IMF because it takes a lot of space to write all of those words. All right. Now, the first thing that I want you to do when you read the word forces, I want you to read forces, that word, as attraction. All right, intermolecular attraction. What we're going to be talking about are the ways in which different molecules are attracted to each other, the way they attract each other, and how they come together. All right. So when you hear the word intermolecular forces, think intermolecular attraction, the attraction that exists between two molecules. Now, there are 3 intermolecular forces that we're going to look at, that we're going to study. We're going to talk about something called London dispersion forces. There we go. London dispersion forces, dipole forces, and hydrogen bonding. All right. London dispersion, dipole, hydrogen bonding. Of these 3 forces, London dispersion is the weakest. So I'm spoiling the ending a little bit. And hydrogen bonding is the strongest. And dipole is the healthy middle. It is stronger than London dispersion, but weaker than hydrogen bonding. All right, and today we'll get through London dispersion. We may not make it to dipole, but we'll pick that up tomorrow. All right, so let's talk about London dispersion forces, or another way to put it, London dispersion attraction. All right, let's talk about London dispersion, I'm going to be abbreviating just as LD. London dispersion. All right. Now, what's at the heart of London dispersion attraction? Right. What kind of attraction are we talking about? Well, I want you to consider for a moment. Think about a helium atom. All right, an atom of helium has 2 protons in the nucleus with 2 neutrons. Or the protons have positive charges. And then in its 1s orbital, oh, here, hang on 1 second. Sorry about that. I was just had to touch base with my wife real quick about a phone call that we were expecting. All right. So we have our nucleus, and then inside our nucleus, we have 2 electrons buzzing around, right? So we've got 1 electron here. And then the other electron will want to be as far away from the first as possible, right? Because like charges repel one another. Electrons are both all negatively charged, and so they want to get away from each other, all right? Now, the thing is, these electrons are constantly in motion, right? They're constantly in motion, and so one of them will move over and push the other one over, and they're constantly just spinning, pushing each other to other sides of the orbitals. And what I want you to do is think about what will happen when one of these electrons moves to this side of the orbital, all right, temporarily. Now, when it does, the other electron will instantly move away, but I want us to pause, to freeze frame. If we're watching a video, pause it and think about the helium atom right now at the split second in time. All right? Before the second electron moves, I want us to consider the state of this helium atom. Which I'm moving over slightly. All right, now, in this helium atom, as it exists right now, both negative charges are on the left side of the molecule. All right? This is another way of saying, we could say that the charges are unevenly distributed in, I said molecule, atom. The charges are unevenly distributed in this atom. The negatives are concentrated on the left side, which leaves the positives concentrated on the right side. And so you could say for this split moment in time that there's a temporary charge separation, right? This isn't the first time we've talked about charge separations in this class. We did it when we were talking about polar bonds, right? How there's a little more negative towards the more electronegative element, less towards the least electronegative element. All right, so right here for this split second in time, we have, oh, hang on. There we go. We have a partial negative charge on the left side of this molecule, and the absence of the electron on the right side of the atom leaves a partial positive charge. All right? This is known as a temporary dipole, right? It's a temporary uneven charge distribution. Now, let me ask you, what do you think this will do to the helium atom, to a second helium atom that is right next to our first? We have a second helium atom with an electron here and another one here. Well, this positive charge is going to attract the electrons, right? This electron is going to move to get closer to that partial positive charge. So in our second helium atom, it's going to create a partial negative on the left side and a partial positive on the right. What do you think is going to happen in a third helium atom? The exact same thing, right? You're going to have your electrons in your 1s orbital attracted to, drawn towards the partial positive. Whoa, drew that a little too big. Creating another partial negative and partial positive. All right? And this attraction right here between the temporary charge separation is London dispersion. All right? London dispersion is the attraction between atoms with temporary charge separation. All right, that is what we're talking about when we're talking about London dispersion attraction. Yeah, they'll almost touch. It's exactly what's going on. All right, that is London dispersion attraction. Now, the reason why this is weak, that this attraction is weak, is because, remember, we did a thought experiment. The electrons are buzzing around, but we paused for a split second when both electrons were on the same side of the orbital, right? Well, once we hit unpause, what's going to happen? This electron's going to move away, right, destroying the partial positives and negatives there, which will chain reaction cause this one to move away, which will chain reaction cause that one to move away, right? You blink your eye and this attraction is gone. It was only temporary, right? It's like that crush that you had on the person for that 1 week of summer camp, but then they left and you left and everyone went home and it was gone. It was dissolved.
Yes,
but
I'm here.
for that, here, sorry, hang on one sec. Okay. Okay. Well, I'll be with you in 1 second. So anyways, that is London dispersion forces, all right? It's temporary, and that's why it's weak. So I'm going to, sorry, my wife needs me, so we're going to go ahead and stop lecture here. We'll pick up tomorrow talking about dipole-dipole forces and hydrogen bonding, and then our last office hours before the exam. Have an awesome, awesome Wednesday, and I'll catch you guys later.